So in this video, we're going to look at the second law of thermodynamics, and that is entropy. So entropy is a measure of the disorder in a system. The more disorder there is, the more favorable that system or that reaction is. And we say that we want a positive value for delta S. So this is different than our delta H. Remember, enthalpy delta H is favorable at a negative. So entropy is positive. An increase in entropy is always favored. Think about if you were to have a glass cup and you dropped it on the ground. It breaks into a bunch of different glass pieces. The disorder has increased. Our classroom gets dirty, all right? So our disorder of our classroom increases. There gets dirt on it. So delta S is going to be greater than 0, meaning positive, when melting, vaporizing. If we have more particles as products, making most solutions, so dissolving is usually, all right, a positive. If we add heat, and if we increase the volume of the gas. These are all examples of processes that increase the disorder of a system. Think about this, melting. This goes from a solid to a liquid where liquids are further apart. All right? So they are more disordered. They are able to move more rapidly and they are more disordered. Okay? So let's look here. When we melt. So the delta S for a solid is positive, even though it is very structured, and because the bond angles change when going from this tight solid to a liquid. When it melts into liquid water, it becomes less organized. So these guys are more able to freely float around, okay, making it less organized. They're able to move around more often, okay? Same thing for vaporization. As I go from a liquid to a gas, my particles move further apart. They are more freely able to move around, becoming more disordered. Remember that gas molecules have low intermolecular forces. All right, so if we're talking about an ideal gas, we say that they have no intermolecular forces. Now we know that most gases do behave as if they are ideal gases. All right, and so therefore they're able to spread out and take the shape of their container. If the products have more particles, all right, our delta S is positive. So let's look at the equation above. I have 2 plus 1. That's 3 moles of products, but I only have 1 mole of reactant. More products means more disorder, just like our classroom gets dirty. All right, more dirt means more disorder. You'll notice that the reactants are solid and the products are gases. So if a reaction goes from more order to more disorder, then we say we have a positive delta S, okay? So not only do I have more moles of gaseous products, I'm going from a solid to a gas, so delta S is positive here. Okay, when we make a solution, remember solute dissolves in solvent, and usually what we're talking about is a solid dissolving in a liquid. And if we were to talk about a salt going in, say, water, for example, that ionic compound, that salt, goes from this very organized crystal lattice structure to individual ions. All right, and these individual ions right here are more freely able to move around. All right, so we are going from this very ordered structure to this disordered structure where ions are able to very freely move around. And this final example here, you can see that our solute, not yellow, the green, I'm sorry, orange. Wow, I'm having trouble with my colors today. The orange has evenly distributed throughout the solvent particles, which are the purple. Delta S, most of the time when making a solution going from a gas and dissolving a gas in a liquid, is less than 0. So it is possible to get a gas to dissolve in a liquid, but we are actually have a delta S of a negative value. So it's not really very favorable. So the fact that it happens means there's something else going on. We're not there yet. We're not at the something else going on part. Okay, let's just look at the delta S. Our gas particles have this very high kinetic energy, and so therefore they are moving super fast. We know they're spaced far apart. They're going to take up the size of their container. But if I take this gas and I dissolve it in a liquid, what I end up doing is I end up restricting the movement of that gaseous particle. Therefore, because its movement has been restricted, its entropy has decreased, meaning it has become more orderly. If I add heat, my delta S is positive. All right, because when I add heat, I am increasing the kinetic energy more than likely if we're in the solid, the liquid, or the gaseous part of it. Now, in my phase change part, that heat is being added. Temperature's not changing, but that heat is going to be used to break those intermolecular forces. All right, so if we go from a solid where our particles are super close together to a liquid where our particles are a little further apart, to a gas where our particles are super far apart, we use heat to break these particles' intermolecular forces, allowing them to be further apart, right? Liquids are further apart than solids, and gases, we've broken all the intermolecular forces. All right, ideal gases have no intermolecular forces. So these guys, we've broken all those intermolecular forces. They are as far apart as possible. They are have the most freedom of movement with a delta S value of being positive. Now, let's go back to our Boltzmann distribution curve from earlier. Remember, as temperature increases, kinetic energy increases, and so does the distribution of that kinetic energy. Okay, so the area under the curve, under each one of these curves is 1. All right, but our distribution, if this is our activation energy right here, the amount as our temperature increases, the curve flattens out. So if this is my 100 degrees Celsius curve, for example, right here, you can see I have significantly more particles that have enough energy to overcome activation energy compared to the blue part of the curve, which is at 0 degrees Celsius. Delta S is greater than 0 when volume increases, because as volume increases, our particles are now have more room to move around, less restrictions. The less restricted they are, the more freely they can move around. Therefore, the more disorder, making it a positive delta S. So let's do some predictions. is the entropy going to increase, decrease, or stay the same? All right, whoops. I have hydrogen peroxide in liquid form, and that is forming liquid water and a half a mole of oxygen gas. So I am going from a liquid, and then I have a liquid and a gas. So ultimately, entropy is going to increase because I have more moles of gas in the product side. All right, in this case, I am taking aqueous hydrogen and aqueous hydroxide ions, and I am making liquid water. So in this case, my entropy decreases because these two reactants join to become a single product. So they go from these ions that are able to float around, okay, independently of each other to a compound. All right, calcium hydroxide solid plus carbon dioxide yields calcium carbonate plus water gas in its gaseous form. Okay, so what do I notice here? I have 1 mole of solid on each side, and I have 1 mole of gaseous on each side. So in this case, entropy does not change because the moles of gas on both sides remain the same. So this reaction does occur, but it does not change the overall entropy. All right. So what I'd like for you to do is I'd like for you to try these next problems. All right, and I'd like for you to pause the video and try these next problems and then come back and let's check our work. Okay, so let's look at our work here. A, I have 1 mole of gas as a reactant and I have no gas as a product. So because I have less gas on the product side than I do on the reactant side, I decrease. Now, in B, I'm going from a solid where this copper sulfate is in these tight crystal lattice structure. Okay, so maybe this is my copper and maybe this is my sulfate. And this isn't really drawn to scale, all right? But we see here that our copper and our sulfate are in these tight crystal lattice structures. Okay, and we now have our individual ions floating around are independently of each other, and so therefore our entropy has increased. Finally, in our third example, I have 1 mole of gas, or I'm sorry, 2 moles of gas as the reactants. I have 2 moles of gas plus an additional mole of gas. So I have 3 moles of gas on the product side and 2 moles of gas on the reactant side. So because my gaseous moles in the product side increase, so does my entropy. So let's calculate the delta S of a reaction using the following equations. And we're going to do this the same way we did the delta H of formation. So the reaction, not the reaction, the formula is the same. We're just simply taking out the H and replacing it with a S, okay? So the delta S of a reaction is the number of moles times the S of formation of products, the sum of that, minus the sum of the number of moles times the S of formation of the reactants. And these values are also found on your reference table. So when we look here, all right, we have the S of hydrochloric acid has 1 mole, and the S of hydrogen gas is a half a mole, and the S of chlorine is a half a mole, and then we plug in our values. Now, if you'll remember from our delta H, the delta H of anything in its standard state is 0. So hydrogen and chlorine are both gases in their standard state. But look here, so you would have put 0 in for delta H. But look here, for S, you'll notice they are not 0. So that 0 only holds true for the delta H. All right, at this point, up to this point. So be careful. The S values you need to find from your reference tables. So when we plug these in and we solve, and again, this is a bracket, so make sure you're using your order of operations correctly. Parentheses 0.5 times 130.57 plus parentheses 0.5 times 229.96. We get 10.035. Now notice here, this is joules per mole. So delta H was in kilojoules per mole. Delta S is in joules per mole. So this is very important. You need to make sure you have the correct units. Kilojoules for delta H, joules for delta S. All right, let's do this next example. So when we look up our S values and we plug them in, 1 mole of calcium carbonate, and calcium carbonate solid is got an entropy of 92.9. 1 mole of calcium oxide solid is an entropy of 40, and 1 mole of carbon dioxide gas is 213.6. When we solve, we get a negative 160.7. So this value is negative. So this is not favorable. This entropy value is positive, so it is a favorable process. So what are we talking about here? What is a thermodynamically favorable process? This is a process which is spontaneous, meaning it happens naturally without the help of any outside system source, no extra help. All right, so what are some examples of spontaneous processes? Water freezes at 0 degrees Celsius. It's just a thing, it happens. If you put potassium chloride in water, it will dissolve. It's highly soluble. Group 1A, potassium, highly soluble. When you get hot, you sweat. This is going to allow the evaporation of water from the skin to lower the body temperature. It happens naturally. Exothermic reactions, this is our delta H is negative, tend to be thermodynamically favorable, right? Because we said that a negative delta H is favorable. Why? Because we are lowering the energy in the system. All right. So our delta H is negative because the bonds of the products ultimately have less energy than that of the reactants, right? So if we were to draw our quick reaction here, and this is our energy. All right, our products have less energy than our reactants. Endothermic reactions can be thermodynamically favorable. Melting of water, meaning going from a solid to a liquid, is endothermic, but that does happen naturally. All right, so it is thermodynamically favorable. So in this case, even though delta H is a positive value, it still occurs. Why? Because we have such a huge increase in entropy when going from a solid to a liquid. So that entropy is going to be what causes and pushes that melting of water in the direction of happening naturally, even though it is absorbing energy, it is endothermic. All right, that entropy still pushes it to happen. A non-thermodynamically favored process is one that requires help. Decomposition of calcium carbonate requires heat. So calcium carbonate is what we call shelf stable. It tends to remain stable in the container in our stockroom. We have to add heat in order for that to happen, for it to decompose. Water does not run uphill. If we need to get water uphill, we have to push it uphill by using some sort of energy source. Heat never flows from a cold to a hot object. Heat always goes from hot to cold. So if a process is thermodynamically favorable in one direction, it is not favorable in the other. So water, we said, does not run uphill. So it is not thermodynamically favorable moving uphill, but it is thermodynamically favorable moving downhill. Okay, so if it's favorable in one direction, it is not favorable in the other direction. So just because something is favorable does not mean it happens fast. Remember, that is kinetics. Kinetics is the study of the speed or the rate. Thermodynamics is not the study of the speed or the rate. Steel does rust, but it is going to take many years for this process to occur because it has a high activation energy, which we call kinetic control. Steel rusts naturally without the help of any outside source. But the speed at which it happens is a fairly slow process. So do not get these two concepts confused. If it happens naturally is not how fast it happens. So the delta S of the universe can be used to determine if something is thermodynamically favorable. So remember, the system is the actual chemical reaction, just the reactants and the products. It's not any intermediates. It's not any parts of those elementary steps that cancel out. It's just the reactants and the products. Our surroundings are everything else. So we have our reaction, and now we have our surroundings. Okay, so the surroundings are what is everything else. So if the delta S of the universe is going to be the system plus the surroundings. So if delta S is greater than 0, it is thermodynamically favorable. If it is less than 0, it is not thermodynamically favorable.